Hello, and welcome to the Actuarial Data Scientists. In today's video, we're going to be deriving something that could just be a memorized formula for this problem. So specifically for this problem, it is totally possible that someone who studied thoroughly just looked at the options and immediately answered the question. However, we're going to assume that you didn't study and you have to come up with the solution on the fly. That being said, I would recommend memorizing what we end up deriving in this video. Sorry, that was my cat. It appears in this question in this past exam, as well as another exam, I forget which one, where you have to use this formula, so definitely worth writing down and being sure to memorize. But that being said, we're going to derive essentially the solution D. So scrolling down, what is that formula? So specifically for this problem, it's talking about a capped exponential distribution. So that is, you have losses that occur following the exponential distribution. However, if, let's say, there's a $1,500 loss, if you were to cap it at $1,000, then you would just say that the insurance company pays out $1,000. So instead of being given the full information, that is that there was a $1,500 loss, you're only told how much did the insurance company pay out. So if you limited the amount of information you had to just how much the insurance company paid out, what would then be your estimate for theta of the exponential distribution, that is the raw loss amounts. So that is taking into consideration losses that exceed what is paid out by the insurance company. So for that, we need to know the formula listed here. So what I have in the middle is the notation used within this problem, and I believe also in the Mahler solutions. However, what I have written down and that I study and memorize for the exam is the notation on the right. They're saying the exact same thing, and I just prefer notation that uses fewer terms whenever possible. So we'll walk through both of these. So I have here a toy example. So we have, let's say, instead of what we have in this problem that is more abstract, we have 5 observations. We know that claims are capped at $1,000, and there is a $100, a $500, and then 3 capped $1,000 payouts. Given that's the case, the notation in the middle, the sum of xi's would be 600, because that's just the sum of xi from 1 to n, where n is the number of non-capped claims. So that's that 100 plus 500 is 600. N is 2 non-capped claims. S is 3. There are 3 claims that are capped, so we don't know the true amounts. They could be 1,000, they could be more than 1,000, we don't know. What is the capping amount? That is U, so that's just 1,000. And then finally, my simplified notation on the right, I just choose to write the summation of xi's. So that is going to be 3,600. So whether it's capped or not, I don't care, just sum it up. And when you do this, you see that they equal each other. So the notation in the middle here, we have the sum of non-capped claims is 600 plus the number of capped claims multiplied by the capped amount. So you see that numerator is just the same thing as summing up all the xi's. And then finally, all of that divided by the non-capped claims. So instead of the traditional sample mean that we would use for the exponential distribution, where we would divide by 5, in this case, we're only going to divide by 2 because there are only 2 non-capped claims. So that is walking through the notation of what ends up just being the solution. I think the n is actually divvied up. So yeah, 1 over n here and then divided by n here, but it's the same thing. Versus the notation I write, because there are fewer moving parts. In terms of memorization, it's easier, but they're saying the same thing. So that's what the notation means. And then finally, what you can choose to do instead is, I'm not sure if the writers of this problem wanted you to have this memorized, or they expected no one to have this memorized and for you to use maximum likelihood to derive this on the fly. I'm guessing it's the latter, but considering it also showed up in another exam, I would say this is a formula worth memorizing for future exams. So in the ensuing solution, we're going to use maximum likelihood estimation to derive that formula that you should memorize, so you don't have to do maximum likelihood estimation. So with that, the first thing is a quick recap of what likelihood is, or maximum likelihood estimation. So what you do is you take the product of all the probabilities of the data, and you are going to choose the hyperparameter. So in this case, we're trying to estimate theta. What choice of theta will maximize the likelihood of having seen the data that we have? So maximum likelihood estimation is saying take the product of all those likelihoods, then take the derivative with respect to theta, and then choose the theta that makes that equal to 0. And then you also take the log of the likelihood just because it makes the math simpler. But at the heart of it, you're just trying to find the theta that maximizes the product of all the probabilities of the given data. So with that said, the reason it's likelihood and not probability is because when you're dealing with continuous distributions, you're looking at likelihoods, that is the PDF value, as opposed to probabilities. So you wouldn't say for an exponential distribution, what's the probability of seeing exactly a $600 claim, because that probability is just 0, so you use the likelihood. Well, we are still going to use the maximum likelihood estimation, but here, instead of the likelihood, we have to use probabilities for the capped claims. So in this notation, the capital pi here, that's just a notation meaning product, so we're going to take the product of all the likelihoods. And I have probability of the given xi. So from 1 to n, so the non-capped claims, that's just going to be the likelihood or the PDF value, so that's as it normally is. However, the 1 to s, so those capped claims, this is going to be 1 minus the CDF of the capped value. And the reason for that is if we see, so back to our toy example, a $1,000 claim, we don't know whether it was $1,000 or $1,500 or $1 million. We have no way of knowing. And so the probability of seeing $1,000 paid out by the insurance company is equivalent to a claim occurring where the loss amount is greater than or equal to 1,000. And so that's just going to be the survival value of U, or 1 minus the CDF. So I love you all. I'm not saying F you, but that's just the way this notation worked out. So we're going to do 1 minus the CDF to get the corresponding probability that a loss was greater than or equal to that value. And so we're still doing the same thing conceptually, right? We're saying take the product of all the likelihoods and probabilities. And at this point, it's just a traditional maximum likelihood estimation. So here we're going to use our knowledge of the exponential distribution. So for this part on the left, from 1 to n, we're going to do the PDF. And then on the right, we're going to do 1 minus the CDF. We then are going to see these ones cancel. And so we're just left with that e to the negative u over theta. At this point, we then say, as always with the maximum likelihood estimation, we're just going to take the log of that. And again, this is because summations are simpler than products when trying to deal with derivatives. And the logarithm is a monotonic transformation. And so when you're trying to find the value of theta that maximizes the overall function, sorry, my cat's playing with something, so I'm going to stop him. Yeah, kitty cat, what are you doing? This is kitty cat. Hi. So that's right. So the logarithm's a monotonic transformation. So we only care about what value of theta maximizes that overall function. And let's say you have some curve. If you add a constant or you multiply it by its scalar, the location of the maximum is going to be the same corresponding value. So that doesn't change anything. So we can take the log, it doesn't change the location or the theta value that will maximize or minimize the function. And for that reason, we can do the logarithm, knowing that our next step is to take the derivative. So we take the logarithm, we see that the logarithm of that product is going to be equal to the summation of the logarithms. Kitty, what are you doing? So that's what we're looking at here. So taking the logarithm of the product and then the summation of the logs. We then are going to break this up, so when you have division within a logarithm, you can say the logarithm of the numerator minus the logarithm of the denominator. So that's all we're doing here. We then can break this up into its two components. So the summation of a constant n times is just going to be equal to n times that constant. And so here we're breaking this summation into just the left component, and the natural log of e to something is just that something. So that's why we just have the summation of negative x over theta minus, and then this is not included in the summation, we broke it out, n times the logarithm of theta. And then finally on the right we get to do the exact same thing. So again we have a constant summed from I equals 1 to s. So we just do s times that constant. So here it's negative s times u over theta. Finally, let's see what we do here. We have the summation of x, and then we pull out that negative 1 over theta. And that's it. So here we're just trying to draw attention to the only thing you really need to know is the summation of xi's plus the number of capped values and what the cap of losses is. So at this point we are now in a good spot to take the derivative and set equal to 0. So we're going to take the derivative of our log likelihood. So that's what we have here. So I'm not sure if I need to walk through this or not, but this is theta to the negative 1, so you drop down the negative 1, the negatives cancel, and then it just becomes theta squared, or log of theta is just going to be 1 over theta, and then same thing for this theta on the right as the first one. So now that we have this mess, we set it equal to 0, and what we can do is multiply both sides by theta, so 0 times theta is still just 0, but then you cancel out these squares and they just become thetas, and this theta goes away. So that's been simplified. We then, let's see, add n to both sides, so this moves to the right, or excuse me, to the left, and then we multiply by theta to get rid of the denominator terms. So we have theta n equals the sum of xi's plus s times u. And then finally we're trying to solve for theta, and so we just divide both sides by n. So at this point we find that the sum of xi's from 1 to n plus the number of capped values times the capped value divided by the number of non-capped claims is going to be a local maxima or minima for theta. So if we wanted to be technical, we would take a second derivative and confirm that this is a maximum, but because we're lazy, we're just going to assume that's the case because it's the only solution we found, and there is no solution option for the question. And then finally what I have here is just breaking it up into its two components, but this is the same thing. And this is just to draw attention to the way it's written in the solutions. And then finally, again, I just have the notation that I write down for when I was studying for MAS 1, because it's less notation and less writing. But that sums it up. That's how you go about deriving the answer, which is D. Again, this is something that I'd recommend you just have memorized for future exams. But on the off chance you didn't, you would use maximum likelihood estimation to derive this on the fly. So with that, thank you, and as always, hope you enjoyed these videos and consider subscribing if you find them helpful. Thanks.